Let's talk about Euler's method. There are three ways to, quote, solve differential equations. First, analytically, we find a formula for the solution. For example, we saw earlier that the solution to the differential equation dy dt plus 2 over ty equals t minus 1 is y equals t squared over 4 minus t over 3 plus c over t squared because it's a linear first order differential equation. So we can find a solution to that. We can solve them qualitatively or graphically, as graphing the solution using a method like slope fields. For example, graph a solution to the initial value problem dy dx equals x squared plus y squared, y of 0 equals 1. If you use slope fields to graph it, you end up with something that looks like this. And then we can also solve it numerically. That's where we're estimating a numerical solution using a method like Euler's method. I haven't explained to you what Euler's method is, but it's the numerical equivalent of what we just saw, solving it by graphing it. So here's an example of Euler's method. Let dy dx equal x squared plus y squared with y of 0 equals 1. Estimate y of 0.5. Use a step size of h equals 0.1. Okay, so let's graph this. We know it goes through 0, 1. We've got this. Suppose we wanted to estimate y of 0.5. So where along this axis are we going to see y of 0.5? So here's the way Euler's method works. I'm going to explain it graphically, and then we'll just do it arithmetically. So what's our estimate for the slope at this point at 0, 1? Well, since dy dx equals x squared plus y squared, if you plug in 0, 1, that just ends up being 1. So our estimate for the slope is 1. So now we're just going to, if the graph through this point is 1, if the slope of the curve to that point is 1, we're just going to keep continuing, and yeah, we'd end up at this point. So if we start off at the point 0, 1, if we just continue this along this line with slope 1, until we get to x equals 0.1, then this would be the point y, equals 1.1. So we'd have 0.1 and a 1.1. Okay, 0.1 and 1.1. Sorry for the sloppy writing there. And then we would repeat the process. We would plug in the point 0.1, 1.1 into here, and we'd find out what the slope is. And then we'd use that, so it's going to be a little bit steeper, and then we'd use that to estimate the y-coordinate of this point. And then we just keep going until we end up with when x equals 0.5. Okay, so here's the equivalent arithmetically. So we want to estimate y of 0.5, given this differential equation, this initial value problem, with a step size of h equals 0.1. So we have this formula, y1 equals y0 plus h f of x0, y0. Now, y0 is, in other words, y of 0. We're going to see that's going to be 1. F of xy is x squared plus y squared, x of 0 equals 0. It's not that x0 always has to equal 0. It's just that here, since we're told that y of 0 equals 1, that means we're going to start off with x of 0 equals 0. That's our starting point. And then y1 is going to be our estimate of y of 0.1. That's our step size. Just as in this graph, first we use y of 0 to estimate y of 0.1, then we use that to estimate y of 0.2, etc. So in the same way, y1 is going to be that estimate of y of 0.1. And we'd use this formula. So y1 is 1, that's y0, plus h, that's our step size, that's 0.1, f of x0, y0. So in other words, it's going to be 1 squared plus 0 squared, or really 0 squared plus 1 squared, same difference. And we end up with y1 equals 1.1. And so, yeah, that gives us the same answer, no surprise there. Now we continue the process, let's say the more general formula. So suppose we're given an initial value problem, dy dx equals f of xy, y of a equals y0, and we want to estimate y of b. We can estimate y of b and y of x for values of x between a and b in the following way. Choose a step size h, subdivide the interval a to b into subintervals of length h. So here we have a, here we have b, and we're going to subdivide this into subintervals of length h. And then we apply this iterative formula, y sub n plus 1 equals y sub n plus h, f of x sub n, y sub n. And again, y sub n is an approximation of y of x sub n. So we do what we've done before. Okay, this is our general formula. That's the general formula we have for Euler's method. And we do what we've done before. We end up with y1 equals 1.1. Okay, now we're going to use that to estimate y of 0.2, in other words, y2. So using this formula, we find that y2 equals y1 plus h f of x1, y1. And x1, y1, that we saw that a moment ago. That's just 0.1, 1.1. We gleaned that from the previous example. Okay, so y2 is our estimate of y of 0.2. We just plug in, n equals 1 into this formula. And we end up with y2 equals y1, in other words, 1.1, plus h, that's going to be 0.1, f of x1, y1, in other words, it's going to be 0.1 squared plus 1.1 squared, which is 1.222. So we end up with x2, y2 equals 0.2 times 1.222. y3, we do the same thing. y3 is y2 plus h, f of x2, y2. This is our y2. H is 0.1, and then we just have f of 0.2, 1.222. In other words, 1.222 plus 0.1 times 0.2 squared plus 1.222 squared. And we end up with this as our y coordinates. So that's our estimate for y of 0.3. So here's our x through y3. And we do the same thing for y sub 4. Here's x through y3. We just found that on the previous page. Here's our formula for y sub 4. Plug in what we know, like y sub 3 and h. F of x3, y3, we end up with this. But again, f of all of this stuff is just going to be 0.3 squared plus 1.3753284 squared. We end up with 1.573482122 for x sub 3. For y sub 3. Okay, and then we use that to calculate x sub 4 and y sub 4. So let's see, so this is our x sub 4, y sub 4. We're going to use that to estimate y sub 5. That's y sub 4 plus h, f of x sub 4, y sub 4. In other words, here's our y sub 4. We have h, which is 0.1 times f of that. F of that is going to be 0.4 squared plus 1.573482122 squared. In other words, we end up with 1.837065536, and that's y sub 5. That is our estimate for y of 0.5.